Hi, I'm Calvin. I created the pigrow garden automation project to help me look after my plants. I've got a few systems currently in use. I'll show them to you in another video, but today I'm going to build one from scratch. Fairly short on space, but I've got this bit of my windowsill free, so I'm going to build a little one that I can use to test some sensors. Then, when it's all up and running, hopefully I'll be able to use it to start seedlings and grow a few microgreens or small herbs. The main objective for this is to develop the self-watering system and to test some soil moisture sensors with it. Though, as it's on a windowsill, I'm going to use the opportunity to test some light sensors as well. I'll show you these in a different video. Today, I'm just going to concentrate on setting up the pigrow using a Raspberry Pi Zero, a Pi cam, temperature and humidity measurements from a BME 280, and the soil moisture sensors we'll be testing. The camera is a really fun and useful feature. By combining periodic photos of the plants, we can create time-lapse videos which will show their growth and how it's responding to various conditions. I'm using a Pi cam for this because it's easy to fit into such a small space, and will give us a lovely crisp clear image even as close as it's going to be. We may need to refocus it using this little thing that comes with it. You can also use a USB webcam. That will just plug into the USB. If you're using a Pi Zero though, you'll need a powered USB hub or it won't be able to give it the correct voltage. The other option is the Pi HD cam. Connects to the Pi using the same ribbon cable, but it does require a lens and they're quite a bit more expensive and we don't really need the extra quality. So for what we're doing, get a really nice clear high quality image. The Pi cam module 2 is perfect for us. Temperature and humidity are probably the most important factors for a grow space, so we'll be measuring them using a BME 280. It's a nice little I2C sensor that's available everywhere fairly cheaply and gives good reliable results. I2C sensors are great because they're very simple to use, and as long as they have individual addresses we can connect lots of different sensors together, so we don't need to worry about using up all the GPIO pins. Also, all the complicated stuff is normally taken care of on the chip. We just get a nice reliable reading without having to worry about calibrating input voltages or anything like that. I'll be testing 3 different soil moisture sensors. They're all capacitive sensors, which means they won't degrade into the soil, unlike these awful bare metal ones. They have at most a lifetime of a couple of months before they stop working. These analog ones are cheap but require an ADC to work with the Pi because the Pi doesn't have any analog pins. There's a lot of good choices for that. I'll be using the ADS1115. I'll also be testing the stemmer from Adafruit and the chirp. Both of these are I2C sensors. They have onboard temperature compensation, so they're going to be a little bit more accurate than the analog one, but we'll be testing them all together and we'll see if there's any functional differences between them. Designing it, the main limiting factor is space. We need the camera somewhere where it will get a good angle and to leave room for the self-watering system, so I'm going to have a raised platform for the plants under which I put the self-watering stuff. And up here on the side I'll have a panel with a Pi cam and all the wiring for the sensors. I've 3D printed some legs to hold up the frame. I've got a little lip to fit over this bit of my windowsill and I'll raise the pots up 90mm. So there should be plenty of room for the watering stuff under here, and if not we can always extend it. The panel for the electronics connects on the side against the wall. The camera is in this little enclosure which is tilted down and slightly inwards, so it gets a nice view of everything. We can replace this with one angle differently if you want to change it later. The BME 280 is in this little gridded enclosure which should allow it to get an accurate measurement, but once it's up and running I compare it to another sensor to ensure it's not affected by the heat from the Pi or its positioning. On the platform I'm going to start by having the pots just sitting in a tray. I'll update this when we make the self-watering system, and we'll be experimenting with different pot sizes, watering methods, soil mediums and all sorts of other things in other videos, but for now a simple grid of pots 2 deep and however many fit lengthwise seems like a good choice. Inside the case is fairly simple. The Pi sits up here next to the camera, so I can connect them with a nice short ribbon cable. The power runs out round here and down, so it exits at the bottom neatly. I designed it with 3 modular panels. This middle one has all the sensor wiring. The I2C connects here, splits off on the left to the ADS1115 and the BME 280 on the right. The soil moisture sensors also connect here, as will the light pole. So there's actually going to be a lot of wires here, but you don't need this much if you're just doing a much simpler system. You can get the same functionality from just 3 sensors, and if they're all I2C, you don't need the ADS1115 at all. Each I2C sensor requires its own unique I2C address, and I was lucky that all those sensors I wanted to use will work together without any issues, though it's important to check as conflicting addresses won't work together. Some sensors do allow you to change, such as the stemmer, which allows you to select between 4 addresses by changing the solder pins on the back, and the chirp, which allows any address to be selected via onboard settings. Though of course you need to set that when it's plugged in on its own. With such a small build, we don't really need to worry about the length of the I2C cables, but I've tried to keep them short, and I've kept them away from the power cable, as though it's only 5V DC. It's best practice not to run power and signal wires together to avoid any risk of interference. The BME 280 I got came with some pins to solder to it. Put them through there, dab of solder on each, but instead of using those, I just soldered some wires directly to it. Put that through there, solder it just as with the pin, and I've just done one to each of the 4 connections we're using. Then they connect to the I2C connection block. It's very simple, just strips of PCB header pins, the same as the ones that came with the BME. Along the bottom I've soldered a bit of wire to bridge the pins, so they all share a common connection. So now, when something connects to one pin, it connects to all of them. I've made it this way because I've got a lot of things to connect, and it's primarily a testing box, so I'll be plugging things in and unplugging them. But for a more permanent build, you could do something much simpler. For example, we could just cut these 2 wires, strip them, join them together, and then we can connect one end to the GPIO and the other 3 to the sensors. So I've got them 1 facing this way, 3 facing this way. The wire's twisted in the middle. I'm just going to put a bit of solder on there. Nice good connection. So now we can plug this into one of the Raspberry Pi pins, and these will split out into the sensors. If you don't want to solder, then you don't need that, and you don't need to make one of those. You can always just connect the wires using a screw terminal. There's all sorts of ones you can find. One of these, I honestly never found those work too well, but if you get a good one, they do work. Or there's always a crimp. I don't have any the right size here, but you get these that are solder-free connections. I mean, this is just a standard crimp that you squeeze, but you get them that have the solder in that you can just heat up with a hot air gun or a lighter. I think they work. We need to set up the SD for the Pi, so on my laptop we need to open a browser and go to raspberrypi.com. We're looking for software, and we want to download the Raspberry Pi Imager. It comes for Linux, Mac and Windows, so get whichever you need. It's only a simple little program, but it makes things very easy, so install that and run it. All we have to do is select the operating system. We're using Raspberry Pi OS, and then select the SD card we want to write it to. Writing the card takes a bit of time, but I'll skip ahead to when it's done. So we can take the card out and put it in the Pi. We don't actually need anything connected to set it up, but I'll show you how to do it headless another time. I've got it connected to a mouse and keyboard through a powered USB hub. Also a screen connected to the mini HDMI, so with the SD in and everything plugged up, we can power it on. You'll see the little light on the Pi start to flicker, show that it's doing things, and the cursor in the top left of the screen starts blinking. The 0 takes a bit of time, especially on its first run, but eventually we see the splash screen appear. Welcome to the Raspberry Pi desktop. And it will load up and start the setup wizard. All simple stuff. Change any you need to. You want to set a new password, but I'll do it later. It will look for Wi-Fi, so select your network. Put in the password. The final step here is to let it update the software. It shouldn't take too long, but it will need some time. So jumping ahead again, and we're done. Now we're connected to the network, you want to note down your local IP address, as we'll need it later. Just hold the cursor over the network symbol in the top right. It says ours is 192.168.0.179. We use this to connect the remote, but before we can do that, there's one last thing. Open the menu and go into Preferences, then select Raspberry Pi Configuration. Then once that opens, we want the Interfaces tab. SSH is how the remote talks to the Pi, so we need that enabled. The sensors we're using are I2C, so we need that enabled also. Press OK and it will write to the system. And that's everything we need to do with the Pi, so we can switch back to the laptop and set everything else up remotely. Back in the browser on the laptop, search for pigrow Windows Remote, which brings us to the GitHub page. I'm reworking the GUI at the moment, so there's also testing versions in here, but we need the newest stable version, so we'll download that. If you're watching in the future, hopefully the rewrite will be complete, and there'll be only one version again, with all of the new features added into it. Follow the pigrow subreddit for updates on that. When it's downloaded, we just need to unpack the zip. Open the folder. We want to run pigrowremote.exe. Sometimes it will warn you it doesn't know who made it, but it was me, so I run it anyway. Up here we put in the local IP address of the Pi we noted earlier and press connect. When it connects, it will have a quick look at the Pi. Sometimes its layout does this, but we can touch the side to fix it. There's a lot of system info here. It recognises it's a Pi 0, no pigrow folder yet of course. If the camera was plugged in, then it'll tell us about it up here. The time matches my computer, so logs will be accurate. Most importantly, there are no power or overheating warnings. It will warn you here if it's detecting undervoltage problems. If so, you'll probably need a better power supply or USB cable. Surprisingly, it is often the cable that's the problem. It'll also warn you about overheating. If so, you'll need to add heat sinks, ventilation or fans to try and keep it cool. Everything's good, so we can get to installing the pigrow software. Click pigrow install to bring up the dialog box. It has to run a few tests on the Pi first, so it takes a second. Almost everything's currently red because it's not installed, and they're all automatically selected, so that's fine. We also need to install the drivers for our sensors. I've only got the BME280 connected, so let's just start with that. We can always come back for the others later. Double click to set install to true. We're not using a DHT, so we don't really need that. Doesn't matter though. Press start and it will begin to download and configure everything we need. Again, depending on your internet speed, this could take a while, and the Pi is pretty slow, so if it looks like it's not doing anything, just wait a little longer. It's not the prettiest dialog box, but rewriting it is right near the top of my list of things to do after I finish this video. So hopefully the new, better looking and easier to use version will be coming soon. Skipping to when it's done, we get the setup wizard. Nothing complicated, it wants us to name our box. It's on the windowsill, so we'll call it that. We might as well let it run the self log, it just records system information if we need it. So that's everything installed. We can go set up our sensor. I had to move everything, so I'm recording the rest of this on a different Pi, but it's still all exactly the same. We want to switch to the sensor tab. At the moment the table's blank, but we can change that by adding our BME. In the drop down there's currently BME 280 and BME 280 new, because Adafruit changed their API. As we've just installed, we've got the new version of their code. The old is just there so it didn't cause problems for anyone already using it. So select that, press Add to open the sensor dialog box. First, let's see if our sensor's working. It's on the default address, so that's fine, and if we press Read Sensor, it will tell us the humidity is 51 and the temperature is 18°C, which seems about right. Now we know it's working, we can give it a name. It's our only BME, so we might as well call it that. If we want to change the log name, we can do that. I'm going to, simply because on this Pi I've already got one using that name. Finally, we have to tell it how often to log the sensor. Every 1 minute will give us plenty of data to test it with, so let's select that. Press OK and add it. It will check we want to update cron. With that done, there it is in the sensor table. It's writing a log every 1 minute, so I'll leave it for a bit and we can gather some data. So now it's had a chance to run for a bit, we can switch to the local files tab. Press download and select logs. We see it's found our BME test log, so we can go and graph it. In the Graphs tab, we select to make it locally. We just need to select log file and choose the BME test log. It fills all the details in for us, so we can just select which bit of information to read. Let's look at the temperature. If we select download, it'll pull the most recent version from the Pi, so I might as well turn that on. Then just press add and it will read through the log and we can see it's found 18 data points, which is 18 minutes of temperature recordings. There's a lot of options for graphs, but let's keep it simple. Make a basic line graph to start with. Just select line from the graphs drop down, press make. Looks like it's been getting a tiny bit colder for the last quarter of an hour, which is about right for this time of day. Over a longer period we'll of course see much more interesting trends, be able to get a really good idea of what's happening in the grow space. After testing I tidied up the wires and soldered them in place. Then I plugged in all the soil sensors. The first section in my panel will be added when I fit the light sensor bar, so it's just a hole for now. The pots are designed to sit lower when I make the self-watering system, so for the sake of testing the camera I made shorter pots, but forgot this would make them a little too short for the soil moisture sensors. Hopefully it shouldn't matter too much though. I also focused the camera and started the time lapse, but we'll come back to that after it's had time to record. With an initial look at the sensors, the chirp shows exactly what we'd expect to see. It's very low until put into slightly damp soil, then after reaching its new level, declines slowly. There's a sudden drop in value where I disturbed everything, which is something to be aware of when switching to sensor-driven watering. There was a bad jumper wire to one of the analog sensors, resulting in bad readings that could also be why they're showing very different behaviours. I'll have to investigate the blue one more, but there's ever so slight upward elevation to the orange, and I think that's what we'd expect with these sensors, as unlike the chirp, we're just getting raw readings of the voltage. The drier the soil, the higher the value. Hence that step down when placed in soil. The Adafruit seesaw stemmer is given a very noisy signal. It did the same when I was writing the pigrow code for it on my test box, so I don't think it's the connection. There's also erratic values, so maybe instead of taking one value and accepting it, I should take multiple, throw out any crazy values and average the others. I'll experiment with that to see if I can get a better reading, but also I'll get another sensor to check if it's normal behaviour. I then gave my plants a good soaking with some water. Of course I should have done this when I potted them up, but I wanted to test the sensors. After watering, the chirp shows exactly what we'd expect to see. A rise in moisture, then a decline as it drains and dries off. The two analog sensors both drop lower, then rise ever so slightly, so we'll see how those do over time. The stemmer doesn't really show that much at all. I think I'll definitely get another one to see if it works any better. But I'll also experiment more with this and see if I can get it giving useful results. Hopefully this video has been interesting. I get to work on the light pole while this gathers some data, and hopefully we'll be ready to start designing the self-watering system when that's done. Subscribe if you want to see more. A big thank you to my Patreons that make this possible, and for more information or to support the project, there are links in the description. I'd love to hear any comments or ideas, either here or in the pigrow subreddit.